If you break your arm, an X-ray gives you this really clean, jagged white line. It's totally binary, broken or not broken.
Right, yeah. And as engineers, we love that kind of decisive diagnosis.
Exactly. We really like finding that single point of failure,
Yeah.
applying the universal patch, and then just walking away knowing the job is done.
Yeah, but if you walk into a commercial kitchen in South Africa today to install water treatment equipment, and you expect that same, like, single decisive fix, you are guaranteeing a catastrophic failure.
Which brings us to our mission today for this deep dive.
Mm-hmm.
We're looking directly at a highly specific, honestly incredibly practical article from the knowledge base on the DWT website.
Mm-hmm.
It's titled Food Service Water, Coffee, Combi Ovens, and Ice. And the entire goal today is to help you, the engineers and technicians, actually specifying and installing these systems on the ground, understand why the whole one-size-fits-all approach is just, well, a total trap.
Yeah, because a commercial kitchen is not a single environment. I mean, it houses 3 completely distinct machines, and they are facing 3 entirely different chemical enemies.
You really have to treat the kitchen as 3 separate patients.
Exactly. You've got the espresso machine, the combi steamer oven, and the ice and beverage station. They absolutely do not share the same rules of engagement.
Okay, so let's unpack this. We're going to start with the espresso machine, mainly because it totally subverts standard technician instinct.
Oh, completely.
Right. Because we spend our whole careers trying to strip minerals out of water. We're taught that pure water is safe water. But if you give an espresso machine ultra-pure, zero TDS water, you basically create a culinary disaster.
You do, because that pure water acts as an incredibly aggressive solvent. I mean, coffee extraction relies entirely on the complex chemistry between the heated water and the roasted bean.
Right.
So if you strip out all the minerals, the water just pulls the wrong compounds out of the grounds. You're left with a cup of coffee that tastes completely flat and aggressively sour.
Which means the technician gets a furious call back from the restaurant owner saying, your expensive new water system ruined my coffee.
Exactly.
And if you look at the actual targets published by the Specialty Coffee Association, the SCA, they're basically demanding we leave the cholesterol in the patient. They publish very hard numbers for what this chemical solvent needs to look like.
Yeah, the SCA targets are just a masterclass in walking a chemical tightrope. They actually want to see a total hardness of around 68 milligrams per liter as calcium carbonate.
Wait, 68?
Yeah. They give a working window of roughly 50 to 175, but 68 is the absolute sweet spot.
Hardness of 68 milligrams per liter as calcium carbonate. That is fascinating because it means we are actively ensuring scale-forming minerals enter the machine's boiler.
Right. It sounds crazy, but you need it. And then what about the buffering capacity?
Well, alkalinity needs to sit around 40 milligrams per liter as calcium carbonate, right?
Correct. Add to that a pH right near 7, a total dissolved solids TDS of around 150 milligrams per liter, and absolutely 0 chlorine.
0 chlorine, okay? So the alkalinity acts as a buffer because without it, the natural organic acids in the coffee beans just completely take over the flavor profile.
Yeah, which is exactly where that harsh, sour taste comes from.
But the tension here is wild. I mean, you want 68 milligrams per liter of hardness as calcium carbonate to physically carry the heavy, earthy flavor compounds out of the bean. But you are feeding that hardness into a boiler that operates at high heat inside a machine that, let's be honest, costs as much as a small car.
It's a very delicate balance. If the water is too soft, the coffee is undrinkable. But if the water strays too far up the acceptable range, toward that 175 milligrams per liter as calcium carbonate limit.
You start baking solid scale onto the boiler elements.
Exactly, onto the elements, the group heads, everywhere.
I can definitely see why a tech looking at a municipal supply with a TDS of like 2,450 would panic and just throw a standard under-counter reverse osmosis system at it. I mean, it feels like the safest way to protect the hardware.
It feels safe, yeah. But applying standard street reverse osmosis permeates to an espresso machine is a massive error. Ours strips the water down to almost nothing.
Right.
So you end up falling way below the SCA window. You lose the calcium you need for extraction and the alkalinity you need to buffer the acids.
Okay, so what's the practical fix for someone working in, say, Gauteng, where the municipal water tends to be fairly hard and pretty heavily chlorinated?
Well, on a standard compliant South African municipal supply, the most mathematically sound engineering choice is a targeted scale control cartridge.
Like an ion exchange or polyphosphate system?
Exactly. Sized specifically for the volume of that coffee machine. because this alters the structure of the hardness so it doesn't bake onto the boiler, but it leaves the mineral content high enough to stay in the SCA window.
Oh, that makes sense.
And then you just pair that with a dedicated carbon block to strip out every last trace of the chlorine.
Got it. So the carbon handles the taste interference and the scale control protects the boiler without starving the extraction chemistry.
Right.
Now, what if the technician is working on a borehole? Or a genuinely terrible municipal line where the TDS is just off the charts and they are basically forced to use RO?
If you use RO, then you strictly must blend. You use a bypass valve to mix a calculated percentage of raw filtered water back into the RO permeate.
Okay.
Or you pass the pure RO water through a remineralization cartridge to artificially build the hardness and alkalinity back up to those SCA targets.
It's just a profound shift in mindset. With coffee, we are actively preserving the chemistry to protect the flavor.
Yeah, exactly.
But the moment we walk across the kitchen to the combi steamer oven, we aren't talking about flavor anymore. We are talking about metallurgical survival.
Yeah.
The rules completely flip.
Oh, yeah. A combi oven operates in a relentlessly hostile environment. High heat, high pressure, constant steam. It's arguably the most specification-driven piece of equipment you're ever going to install.
And here is where technicians make their biggest diagnostic error. I mean, if you ask an engineer what the primary threat to a steam generator is, the immediate answer is almost always hardness.
Always. They assume calcium scale is what's going to ruin the oven.
Right. But it isn't.
No. I mean, scale is certainly a nuisance. It forces the kitchen to run descaling cycles, which costs time and chemicals. But scale does not destroy the machine.
Yeah.
The true assassin in a combi oven, the element that will literally eat the stainless steel alive, is the chloride ion.
And just to be incredibly clear here, we are not talking about chlorine, the municipal disinfectant.
No, definitely not.
We are talking about chloride, the naturally occurring negative ion found in dissolved salts. So how does chloride actually destroy a steel boiler?
Well, under the high temperatures of a steam generator, the water boils off, right? But the chloride stays behind and concentrates.
Okay.
And chloride ions are incredibly small. They have this severe electrochemical affinity for the protective passivation layer on stainless steel. So they attack microscopic imperfections in the metal, basically breaking right through that protective layer.
Creating pitting corrosion.
Precisely. Pitting corrosion. Once they create a microscopic pit, the environment inside that tiny hole becomes highly acidic. Wow.
Yeah, and that accelerates the corrosion even further. It just bores a pinhole right through the wall of the steam generator. Plus, it causes stress corrosion cracking at the welds. It is totally irreversible structural damage.
Which completely explains why the manufacturer specifications read like quarantine protocols. Let's actually look at the Convotherm C4 technical requirements from the article.
Yeah, Convotherm sets a pretty wide acceptable range for hardness between roughly 70 and 360 milligrams per liter as calcium carbonate.
So they can handle some scale.
Exactly. But their limits for corrosive elements are brutally strict. Chloride must be at or below 60 milligrams per liter. Free chlorine, at or below 0.2 milligrams per liter. And the pH has to sit between 6.5 and 8.5.
And they also include this really fascinating electrical requirement, a minimum conductivity of 20 microsiemens per centimeter.
Yes.
We definitely need to dissect that in a moment. But Rational ovens use the exact same logic for their boilers, right? Oh yeah, Rational's documentation is just as aggressive. They mandate carbon filtration. The second free chlorine touches 0.2 milligrams per liter. And they explicitly demand reverse osmosis the moment chloride climbs past 80 milligrams per liter.
That's intense.
It is. And what's really fascinating here is how often technicians unwittingly build a trap for themselves by focusing solely on the hardness and just completely ignoring those chloride limits.
The bare softening trap.
Yes.
So a tech arrives on site, tests the tap water, gets a high hardness reading, and installs the standard base exchange water softener. The water tests soft, the glasses look clean, and the technician thinks they've saved the combi oven.
Right.
But a year later, the boiler is destroyed by pitting corrosion.
Because you have to look at the mechanism of a base exchange softener. It operates on a simple swap. The resin beads inside the softener are loaded with sodium ions.
Okay.
When hard water flows through, the resin grabs the positive calcium and magnesium ions out of the water and releases the positive sodium ions in their place.
It only trades positive ions.
That is the fatal flaw. Chloride is a negative ion.
Oh, wow.
Yeah, so the softener resin completely ignores it. The chloride flows straight through the softener untouched. By removing the scale-forming minerals, you've fed the steam generator a diet of beautifully clear, perfectly soft water that is still fully loaded with its primary attacker.
You essentially cleared the battlefield so the assassin could work without any interference.
That is a great way to put it.
The softener solved the nuisance, but left the lethal threat unchecked. So if the South African source water has a high chloride count, which, is incredibly common in coastal areas, bare softening is basically engineering malpractice.
It really is.
Yeah.
Which leads technicians right into the second trap. They realize chloride is the issue, so they install a full reverse osmosis system and send completely demineralized ultra-pure water into the combi oven.
Which violates that specific convotherm requirement we flagged earlier, the minimum conductivity of 20 microsiemens per centimeter. Why is ultra-pure water functionally useless to a combi oven?
Because it fails mechanically. See, steam generators don't use mechanical floats to measure water levels. They use electronic conductivity probes.
Okay, so what are those exactly?
They're essentially two metal prongs extending into the boiler. The machine passes a tiny electrical current between them to confirm the water level.
But pure water doesn't conduct electricity.
Exactly. The only reason water carries a current is because of the dissolved mineral ions acting as a bridge.
Oh, so if you feed the oven fully demineralized RO water, there are no ions to carry the current.
Right. The circuit cannot close. The oven's computer registers that the steam generator is empty. Even if water is actively overflowing out of the vent pipe, it just goes completely blind.
That's wild. And add to that the chemical reality that ultra-pure water is highly unstable. It acts like a hungry solvent.
Yeah.
It'll aggressively leach metal ions directly out of the oven's own copper and steel components just to satisfy its chemical imbalance. So if a technician is standing in a kitchen with a high chloride municipal supply, and softening leaves the chloride, but full RO blinds the machine, what is the actual treatment train?
The only viable engineering solution is reverse osmosis combined with a precise blending valve.
Okay, how's that work?
You use the RO membrane to crush the chloride levels down to single digits, well below the 60 or 80 milligrams per liter threshold. Then you open the bypass valve to bleed a controlled volume of raw, filtered municipal water back into the pure RO line.
You purposefully contaminate the pure water just enough to hit that minimum 20 microsiemens per centimeter target.
Yes. That way, the probes can read the water level. The water is no longer an aggressive solvent, but the chloride concentration is still too low to cause pitting.
You're dictating the chemical parameters rather than letting a blind filtration method dictate them for you.
Exactly.
It's brilliant. Really targeted engineering. So we've secured the heated applications, we kept the minerals for coffee flavor, and we blended the water to save the combi oven's metallurgy. Now we transition to the third zone of the kitchen, the ice machines and the post-mix beverage stations. Here, the thermodynamic reality changes entirely.
It does, because there is no boiling in this zone. The water is served completely unheated.
Which means we lose the two primary benefits of heat. We don't have boiling temperatures to drive off volatile chemicals like chlorine, and more importantly, we don't have heat to pasteurize the water.
Yeah, so the priority matrix immediately shifts to taste, odor, and severe microbiological control. Manufacturers like Hoshizaki and Manitowoc center their installation requirements for ice machines around the NSFA NSI 42 standard.
Let's actually translate NSFA NSI 42 into physical hardware for the technician. What does that mean on the ground?
It dictates a nominal 0.5 micron sediment capture combined with verified reduction of aesthetic chlorine. You must deliver water that is physically free of suspended particulates and chemically stripped of the disinfectant that makes ice smell like a municipal swimming pool.
Right. But wait, earlier you mentioned that scale control is still highly relevant for an ice machine. If the water isn't boiling, why do we care about calcium carbonate scale? Doesn't scale only form under high heat?
That's a huge misconception. Heat accelerates scaling, sure, but freezing forces it through concentration.
How so?
When water flows over the chilled evaporator plates of an ice machine, the pure H2O molecules freeze first. The dissolved minerals don't fit into the ice crystal structure, so they get rejected into the surrounding liquid water.
Ah, so the remaining unfrozen water gets progressively harder and harder as the cycle runs.
Exactly. And the critical failure happens during a harvest cycle. To release the frozen cubes, the machine has to briefly warm those cold plates. It typically reroutes hot, high-pressure refrigerant gas directly through the evaporator coils.
So you have a highly concentrated, mineral-dense film of liquid water sitting directly against a plate that suddenly spikes in temperature.
Yeah, and that thermodynamic shock causes the concentrated calcium carbonate to instantly precipitate out of solution and bond to the metal. Over hundreds of cycles, this thin layer of scale builds up. And scale is an excellent thermal insulator. It prevents the cold plates from effectively freezing the water in the next cycle, and it creates a rough surface that physically traps the cubes, preventing them from dropping during the harvest.
It completely disrupts the mechanical rhythm of the machine.
It does.
So if a technician is working in an area with high hardness, they must include a targeted scale-inhibiting cartridge, usually polyphosphate, right, ahead of the ice machine, specifically to lubricate that harvest cycle.
Right. The polyphosphate coats the scale-forming minerals, preventing them from agglomerating and bonding to the plates when that heat shock hits.
That brings us to the post-mix lines, the fountain drinks. This is really the ultimate test of unboiled water engineering. Coca-Cola publishes a food service specification that leaves zero room for interpretation.
None at all.
If you want their syrup to taste the way their beverage scientists engineered it, you must hit their targets.
The hard numbers for Coca-Cola fountain setups are strict. 0 coliforms per 100 milliliters. Turbidity at or below 0.5 NTU. Total chlorine at or below 0.5 milligrams per liter. Alkalinity at or below 150 milligrams per liter. And TDS at or below 500 milligrams per liter.
Let's look at the physics and biology behind those first three limits. 0 coliforms is non-negotiable.
Oh, absolutely.
Because this water is mixing with sugar-rich syrup in unboiled plastic lines, any baseline bacteria will just rapidly bloom into thick biofilm inside the fountain dispenser.
Yeah, it's a nightmare. And the turbidity limit is equally critical, but for physical reasons. Turbidity at or below 0.5 NTU means the water is optically flawless.
Right.
Any suspended dirt or microscopic grit passing into that carbonator acts as a physical nucleation point.
Because the dissolved carbon dioxide needs a rough surface to break out of solution.
Exactly. If the water is full of 1-micron dirt particles, the CO2 latch onto them and instantly turns to gas, and the beverage foams wildly over the top of the cup before it's even half full.
Nobody wants that. And total chlorine must be below 0.5 milligrams per liter because chlorine chemically reacts with the volatile organic compounds in the beverage syrup, right?
Yes, it strips out the subtle flavor notes and leaves this really harsh medicinal aftertaste.
So what's the practical on-the-ground solution for a South African technician piping a post-mix station? Assuming the local municipality is delivering water that fits the basic alkalinity and TDS limits.
You need a high-capacity certified carbon block filtration array. A properly rated carbon block easily handles the 0.5 micron physical filtration to drop the turbidity, while providing the necessary contact time to chemically absorb the chlorine.
Got it.
It delivers that neutral, sterile baseline the syrup requires.
We started by declaring that treating a commercial kitchen as one unified problem guarantees a failure. I think the mechanics we've unpacked prove that beyond a doubt.
Oh, definitely. The espresso machine demands we carefully curate the hardness and alkalinity. The combi-oven demands we violently strip out the chloride without destroying the electrical conductivity. And the ice and beverage stations demand surgical removal of chlorine and sediment to protect the harvest thermodynamics and prevent carbonation foaming.
Which gives us the unified strategy for the professional technician. Test the water supply thoroughly, and then split the treatment trains.
Exactly. Carbon and scale control for the coffee to stay inside the SCA window. Chloride-driven RO with blending for the combi oven to protect the stainless steel, avoiding the bare softening trap at all costs. And robust carbon block filtration for the unboiled ice and beverage zones.
But there is one final, intensely practical shared element that makes absolute sense, especially in the South African context.
Yes. A heavy-duty shared sediment pre-filter installed directly at the incoming mains before the water splits to any of these specialized treatment trains.
Because of our infrastructure realities. Anyone who has worked a maintenance contract in South Africa knows exactly what happens during load shedding or a municipal pipe repair.
Yeah, the power cuts, the pump station shut down, and the water pressure in the municipal mains drops to zero.
And when the power comes back, the massive industrial pumps kick back on violently. The sudden surge of water, the water hammer, it scours the inside of the aging municipal pipes.
It strips decades of built-up rust, mud, and biological sludge right off the pipe walls and sends it straight down the line.
Yep.
If you don't have a sacrificial sediment pre-filter waiting at the back door of the kitchen, That massive slug of mud will hit your carefully engineered treatment trains.
It'll just instantly blind the zero point 0.5 micron carbon blocks protecting the post-mix. It will foul the RO membranes protecting the combi oven, and it'll completely choke the scale inhibitors feeding the coffee machine.
Exactly. You use a cheap, easily replaceable high-micron pleated filter at the door to take the impact of those municipal pressure surges, protecting the expensive precision chemistry happening under the counters.
It is the ultimate real-world insurance policy. We open this deep dive talking about the desire for a clean, simple diagnosis, the X-ray analogy. It turns out commercial water treatment is highly precise, but the precision isn't found in a magic bullet. It's found in respecting the distinct metallurgical and chemical realities of every single piece of equipment.
The diagnosis is really only murky if you refuse to acknowledge the different mechanisms operating in the kitchen.
Which leaves me with a final, slightly provocative thought for you to chew on. Think about the service call logs at any major hospitality group.
Okay.
If installing a standard water softener secretly causes pitting corrosion in combi ovens, and if standard reverse osmosis makes flat, acidic coffee that drives away customers, and if failing to manage harvest cycle scale traps ice cubes and burns out compressor motors.
It really makes you wonder.
It does. How many thousands of expensive, repetitive service calls in this industry are being written off as faulty machines when they're actually just self-inflicted wounds caused by fundamentally misunderstood water chemistry? You fix the water, you fix the kitchen.